Hello and welcome back. We saw in the last video that delta S for the surroundings, so remember delta S total is equal to delta S for the surroundings plus delta S for the system, okay? And so we saw that we could define delta S for the surroundings as delta H for the system, or negative delta H for the system over T, okay? And so that would give us delta S total is equal to negative delta H for the system over T plus delta S for the system, okay? So remember, if our total delta S is positive, then our reaction will occur spontaneously. If the delta S for the surroundings plus the system is positive, the reaction occurs spontaneously. But we can't measure delta S for the surroundings. We can't quantify that. And so in order to quantify that, we want to put that in terms of delta H for the system, something we can actually quantify. And we saw that we have this definition here. So if we rearrange this equation, we get negative delta T times delta S total is equal to delta H for the system minus T delta S for the system. So we can also look up that delta G is equal to negative T delta S total, okay? And so we can replace that with delta G, and that gives us a new equation with everything in terms of the system itself. So delta G is equal to delta H minus T delta S. And delta G is defined as Gibbs free energy. So that's the free energy of the system, and if that's negative, then the reaction will be favorable. If it's positive, then the reaction will not be favorable and won't be spontaneous. Okay, so a negative delta G means the reaction favors products. A positive delta G means the reaction favors reactants. And so we can use this equation to do some very simple calculations, and we can also use it to qualitatively study a system and see whether our reaction will be favorable or not, or spontaneous or not. Okay, so let's consider the following reaction, which is spontaneous. Okay, we've got 2 moles of starting material going to 1 mole of product. Okay, so our delta S is what? Delta S is going to be negative because we've got 2 moles going to 1 mole. Okay, so what does that mean? It means if we multiply negative T times a negative delta S, we're going to get a positive overall term for our T delta S. Okay, so that means we're going to have a competition between our delta H and our T delta S, which means that delta H must be negative. Okay, so if delta H is a larger negative than the T delta S term, then delta G will be negative overall. In other words, the entropy of the surroundings is increasing more than the entropy of the system, and therefore the delta G will be negative, because remember that delta H term is really talking about the entropy of the surroundings. We've put it in terms of entropy of the system. Okay, so we can look at that on an energy diagram. We can say delta G is negative, so we can put delta G on the y-axis and our reaction coordinate, or our progress of reaction, on the x-axis, and we can see that our starting materials are going from we're going from starting materials to products, and the products are at a lower energy level. So our delta G is negative. When delta G is negative, that's called exergonic. Okay, instead of exothermic, we've got exergonic, and that means the reaction is favorable. So most exothermic reactions are favorable, but not all. We're going to see that we can have a competition there. But exergonic reactions are always favorable. So we don't have enthalpy. We don't have H on this axis, okay? We've got G. We've got, we're representing free energy rather than enthalpy on the y-axis. So if a process has a positive delta G, the process is non-spontaneous and therefore endergonic. So we've got our starting materials at a lower energy than our products. So our starting materials are going to be at a lower starting point. So they're down here, and our products are up here at a higher free energy. And so our reaction is going to be consuming energy. Okay, and so that's going to be a positive delta G, which means it's endergonic, which means it favors starting materials. So let's consider an exergonic process with a negative delta G, which means the products are favored. And so what we have is we've got some, well, let's just define our axes here. Again, we've got free energy on the y-axis. We've got progress of reaction on the x-axis. And we start with just A and B. We've got no C and D. So here's our overall reaction. A plus B goes to C plus D. That's our reaction. So our starting materials are A and B. Our products are C and D. Okay. So we're starting with our starting materials at A plus B at some energy. And as this reaction begins to occur, some of our A and B are going to be going to C and D, right? And once we start building up C and D, then some of them may have enough energy to go backwards and reform A and B. So this is a reversible reaction. A and B is forming C and D. C and D is forming A and B. So we're going to reach an equilibrium where we'll have a certain concentration of starting materials and a certain concentration of products, okay? So a spontaneous process means there will be more products than reactants at equilibrium. So the greater the magnitude of delta G, the greater the equilibrium concentration of products will be. So if you have a very small negative delta G, then you're going to have more reactants than if you had a larger negative delta G. So if your delta G was more negative. Okay, so we'll look at some examples of that. Maybe it'll be a little bit clearer. So an exergonic process doesn't generally give us 100% products. Some reactants will usually still remain at equilibrium. So as we begin to form, as we start at A plus B and we begin to form C and D, okay, then C and D begin to build up, okay, and as C and D builds up, then C and D begins to form A and B until we eventually reach some minimum value that's the most favorable, and that's our equilibrium concentration. Okay, so eventually we reach an equilibrium where the rate of formation of products is equal to the rate of the formation of the reactants, okay? But that's not the concentration. And so we saw this in general chemistry, that the KEQ gives us an idea of the degree to which a reaction is favors products or reactants. Okay, so at equilibrium, the concentration of products over reactants is going to be equal to the KEQ. And we can define delta G in terms of KEQ, where delta G is equal to negative RT, where R is the gas law constant, T is the temperature, times the natural log of the KEQ. Okay? And these are all thermodynamic terms. They describe the stability of the products and reactants, but not the rate at which they're formed. So, for example, a carbon is always forming diamond, or sorry, I got that backwards. So a diamond is always going to carbon at atmospheric pressure, but that process is very, very slow. That's why the ring on your finger doesn't spontaneously turn into charcoal while you're wearing it. All right, so notice that increasing or decreasing the value of delta G by about 6 kilojoules per mole corresponds to a 10 times change in the equilibrium constant. Okay, so if our delta G is negative 17, our KEQ is going to be 10 to the third, and the products at equilibrium are going to be 99.9% products at equilibrium. Okay, if our delta G is negative 11, our KEQ is 10 to the second, 99% products at equilibrium. Negative 6 for our delta G gives us 10 to the first, which is 90% products at equilibrium. And this is an important one here. If our delta G is 0, then our KEQ is going to be 1, according to that equation that we just saw here, okay? If delta G is 0, then our KEQ is going to be 1, okay? And that's going to give us 50% products and 50% reactants at equilibrium. So in other words, if the KEQ is equal to 1, then that ratio of products to reactants at equilibrium is going to be, products are going to be equal to reactants at equilibrium, giving us a ratio of 1. Okay. If our delta G is positive 6, then our KEQ is 10 to the negative 1, and that's going to be 10% products at equilibrium. So we're favoring reactants. Positive 11 gives us negative 10 to the negative 2, 1%, and positive 17, 10 to the negative 3, that's 0.1%. So the most important takeaway from this is to see that if we have a negative delta G, we're going to have more products at equilibrium than we have reactants, okay? And the more negative it is, the more products are going to be favored, okay? If we have a 0 delta G, then our KEQ is 1. We have 50-50 ratio of products to reactants at equilibrium. If our delta G is positive, then we're going to have we're going to favor reactants at equilibrium, and therefore the more positive it is, the more we favor reactants, okay? So recall that a negative sign for delta G tells us a process is product favored or spontaneous. Okay, that does not tell us anything about the rate or the kinetics for the process. It doesn't say anything about how fast a reaction will occur. So some spontaneous processes are fast, such as explosions, and some are slow, such as carbon in the form of a diamond going to carbon in the form of graphite. And this takes millions of years, even though it is a spontaneous reaction. So the reaction rate is a function of the number of molecular collisions that will occur in a given period of time, which is affected by the following factors: the concentration of reactants, the activation energy, the temperature, the geometry or sterics, and the presence of a catalyst. Okay, so all of these things can affect that rate. Rate is determined by using the rate law. Okay, so rate is equal to some rate constant times the concentration of the reactants. And again, we're not going to be doing a lot of calculations with this. We may see a couple of them, but mostly we want to get a qualitative understanding of what's going on here. Okay, so our rate is equal to some K times the concentration of reactants, or the starting materials. And the rate is going to be dependent then on that rate constant. So the degree to which a change in reactant will affect the rate is known as the order. Okay, so let's look at what that means. The order of a reaction is represented by the X and Y in the equations here. So in other words, rate is equal to K times the concentration of some A raised to the power of X times the concentration of B raised to the power of Y. Okay, so let's look at some examples of that, so maybe it'll be a little clearer. If the rate is equal to K times the concentration of A, okay, to the first power, okay, then that's called a first order reaction. So if we double A, we double the rate. If the rate is equal to some K times the concentration of A times the concentration of B, and each of those are to the first power, then we can add those exponents together to get a second order equation, where if A is doubled, the rate is doubled again. If B is doubled, the rate is doubled, okay? But what happens if we double A and double B? We quadruple the rate. Okay, that's why it's a second order equation. If the rate is equal to some K times A squared times B, then if A is doubled, the rate is quadrupled. If B is doubled, then the rate is doubled. Okay. So we can also say, and this is not really covered in your book specifically, that an equation like this one on the right here is second order with respect to A and first order with respect to B. In fact, we probably should write that down. Second order with respect to A and first order with respect to B. Okay, but it's third order overall. And you may see that in some questions outside the book, or I don't know, maybe even in Wiley Plus. So it's important to understand that this is second order with respect to A, which means that if you double A, you quadruple the rate. For example, if A was started out to be a concentration of 2 moles per liter. Then if you double that to then 2 squared is 4, right? So if you double that, then you're going to have 4, and 4 squared is 16. So you're going to be quadrupling the rate. Okay. So, but however, if you just double, say, B, then you're just going to be doubling the rate. Okay, the next thing that's going to affect the rate constant is the activation energy. So we're talking about factors that affect the rate constant. Okay, the second thing is activation energy, or the energy barrier between the reactants and products. So we talked about energy diagrams where we've got some reactants or starting materials going to products, and as we go along that progress of reaction here, okay, then we go through a state where we have some kind of a hump. Because if we didn't have a hump there, everything would just explode, right? We wouldn't have any inhibition to that reaction occurring. But we have to go through some energy in order for the reaction to proceed, and that is called the activation energy, and that goes from the reactant's energy level to the top of this hump here. That's called the activation energy. So the activation energy is represented by E sub A, and that's the minimum amount of energy required for a collision to result in a reaction. That's the energy we have to get over, the hump we have to overcome in order to go from reactants to products. Okay? As the activation energy increases, the number of molecules possessing enough energy to react increases. So we've got number of molecules here versus activation energy, and we may have more molecules at a lower energy. Okay, they don't have that energy that's high enough to get over that energy level to go on to products. We may only have a certain number of molecules here, a small number, that actually have enough energy to go to products at the temperature that we're talking about. So if we lower the activation energy, we can lower the rate, because the molecules will need less energy to get to products. The reaction on the left has a lower activation energy than the reaction on the right. So the reaction on the left is going to proceed at a faster rate than the reaction on the right. The reaction on the right will go at a slower rate because the molecules have to overcome a higher energy level in order to go to products. Okay, another factor affecting the rate constant is going to be the temperature. So raising the temperature is going to increase the rate of the reaction. At high temperature, molecules have more kinetic energy. Okay, so like we were talking about earlier, at a lower temperature, we may only have a smaller number of molecules, the ones to the right of this EA here, that have enough energy to go to products. But if we raise the temperature, we're going to increase the number of molecules in that system that have enough energy to go to products and produce the reaction, because at higher energy, molecules are moving at a faster rate, at higher temperature, I'm sorry. The next consideration, but I didn't mention this, generally, if you raise the temperature of a reaction by 10 degrees, then you're going to double the rate of the reaction. And that isn't true for every reaction. We're going to see some reactions that actually go at a faster rate if you decrease the temperature, and that has to do with our delta G that we talked about earlier. There are also some steric considerations. So steric hindrance and the geometry of compound affects the rate of the reaction. So when molecules collide, they have to have the correct orientation for bonds to be broken and formed, okay? And if a conformation of a molecule is high energy, then it's going to spend less time in that conformation. And so the probability of a collision resulting in a reaction is low. And so we're going to look at that a little bit later on in chapter 7. But remember from the last chapter we talked about, say for cyclohexane, most of the time it's going to spend its time in a chair conformation, not a boat conformation. If it needs to be in a boat conformation to perform the reaction, it's going to be less likely. So we're going to see some examples of how sterics interfere with reactions a little bit later on. So how can we reduce that activation energy? We can do that with a catalyst. So catalysts also affect the rate of a reaction because they lower the activation energy and they speed up the rate of a reaction without being consumed. So enzymes are catalysts. They're a type of catalyst. There are other types of catalysts as well. Catalysts provide an alternate and faster pathway for a reaction. So if the reaction in blue normally has to undergo a high activation energy to go through this high energy state to get to products, if we use a catalyst, we can lower that energy state and allow the reaction to occur much more quickly. It's going to go through a different pathway, and that's why we have this this wavy line here. It may not go through the same exact mechanism to get to products, but it may go through a different kind of pathway, but it's going to the catalyst will lower the activation energy and allow that reaction to occur much more quickly. Okay, so reading energy diagrams. So we're going to bring all of this together in just a few minutes. We talked about energy diagrams a little bit, and remember from general chemistry that kinetics and thermodynamics are completely different concepts. So kinetics talks about how fast a reaction occurs, okay, or the rate of the reaction. So we're really mostly talking about the activation energy here on this energy diagram. How high is that activation energy? How high is that barrier that we have to overcome? And thermodynamics is talking about stability at equilibrium. So how much more stable are the products than the reactants at equilibrium? So how much of a favorable energy gain do we get out from having those reactants form products? And so if we get a larger negative delta G, then we're going to have a more stable system at equilibrium for our products. So sometimes we can have a competition there as well. So we can have A and B going through this activation energy. Let's call that EA1 to give us C and D. Okay. And we can have A and B perhaps going through a different pathway. And let's call that EA2 to give us E and F. Okay. The pathway involving EA2 is higher energy than EA1. And also C and D or let's say E and F are higher energy than C and D. So it's faster to form C and D, and it's lower energy they're lower energy in the end. So we're having a larger, sorry, that's not a very straight line, a larger delta G to form C and D. Okay, we get a more negative delta G, and the reaction's going to happen faster because we have a lower activation energy. So the formation of C and D from A and B is both kinetically and thermodynamically favored. But what if we have an energy diagram that goes like this? We have A and B that can form either this C and D or this E and F. Okay? So A and B is going through a lower activation energy to form E and F than it is to form C and D. Okay? So it's faster to form E and F than it is C and D. So E and F is faster. Okay? But C and D is at a lower energy at equilibrium. So C and D are more stable. So what does that mean? It means that E and F is the kinetic product because it's going to form faster, but C and D is the thermodynamic product because they're more stable. Okay, so E and F is kinetically favored, but the formation of C and D is thermodynamically favored. So if we have a lower temperature, we don't have enough energy to form C and D, we're going to prefer E and F. But if we have a higher temperature, if we put enough energy into that system, and we allow the products to equilibrate, we're going to form C and D because they're more stable. And in reality, we're going to form both products, probably both sets of products, but we get a competition between those things. So as we look at energy, and this could be generally this is G, free energy, but it could be enthalpy as well. Sometimes we look at enthalpy versus progress of reaction. We can go through a lot of different pathways to get from starting materials to products. And I try to keep in my classes everything pretty simple. As far as energy diagrams goes, I like to keep it down to 1 or 2 humps, right? But we see these little humps and valleys in energy diagrams. So what do they mean? Well, we have starting materials here going to this first little valley, okay? So that first valley is our first kind of a temporary product, and that temporary product is called an intermediate. And so that's going to be our first activation energy in this diagram, okay, that we have to go through to get to that intermediate. And at the high point of that activation energy, we have what's called a transition state. Those are very brief, fleeting states for the molecule, or brief, fleeting species that aren't true products, and they don't hang around very long. Okay, and we have to go through that transition state to get to what's called a true intermediate. And these intermediates generally don't hang around long either, but they're generally longer lasting than the transition states. So in the transition states, we have bonds forming. That's where our bonds are forming, and our bonds are breaking. And in the intermediates, we have a true species that has completely broken or formed its bonds. But it's still not our final product, and generally it's very fleeting as well. Okay, so the transition states are at the peaks, and the intermediates are at the valleys, and the activation energies are going from the valleys to the peaks. Okay, well, this one is a little lower. Okay. So transition states are the high energy state that a reaction passes through, where we have these bonds breaking and these bonds forming. So here we're going from this methyl bromide plus the chloride to methyl chloride plus bromide. So we're going through from these starting materials to these products. Okay. So we're going to go through this activation energy. And along that pathway, we have this high point that is a transition state. We don't have any intermediates in this reaction pathway. And in that transition state, we have our bonds breaking and our bonds forming. We're going to study this particular reaction in the next chapter, but don't be too worried about what that transition state looks like right now. What we're just looking at is the definitions here. So transition states are the high energy state a reaction passes through. They're fleeting and can't be observed. Okay, so on an energy diagram, transition states are the maxima, and they represent the transition as bonds are made and broken. Intermediates are the valleys in the energy diagram. So here we have energy versus progress of reaction. And here we have a slightly different pathway. Okay, we've got a similar reaction. We're going from this bromide, this alkyl bromide to plus the chloride ion to the alkyl chloride plus bromide. Okay, so we're going through this activation energy here, this first activation energy to reach an intermediate. Okay, and then we go through a second activation energy. Forgot to draw the little arrow here. To get to the products. Okay, so we've got an intermediate right here in the middle in this valley. We've still got our transition states up here at the top where our bonds are breaking and forming. But see, in the intermediate, we don't have bonds breaking and forming. That's a true species. It may not be very stable. It won't hang around very long, but it's still a true species with bonds fully broken and fully formed. All right, so this topic is a little bit more challenging perhaps to understand, but this is the Hammond postulate. So if we look at 2 points on an energy diagram as we're going from starting material to products, okay, as we move right along this reaction coordinate, okay, if we consider any 2 points that are closer in energy, okay, should be more similar in structure. So here we have our bonds that are breaking and forming here in our transition state. As we move along the path, the bonds are breaking more and more until we get the bonds fully broken. Okay, so depending on whether the reaction is exothermic or endothermic, we can make some assumptions about that structure of the transition state. Okay, so for an exothermic reaction, the transition state is going to more closely resemble the reactants because it's closer in energy to the reactants. And for an endothermic process, the transition state is going to be closer in energy to the products, so the transition state is going to resemble the products more. Now, generally, I don't ask my students questions about the Hammond postulate on exams, but you know, just to kind of cover it since it's in the book, you maybe ask something on the homework with this. But the transition state that's closer in energy to the products is going to favor the products more. It's going to look like the products more if it's endothermic. And a transition state, if it's exothermic, is going to be closer in energy to the reactants. So it's going to favor the reactants more. It's going to actually look like the reactants more. Now, we've talked about a lot in this section of this chapter, but we want to kind of bring it all together with these 4 questions. Or, well, these few questions. It's actually more than 4 questions, but let's see if we can bring all of this together, okay? Compare energy diagrams A and D. So that's this one up here at the top and this one down here at the bottom. Assuming all other factors are identical for the 2 processes, identify which process will occur more rapidly and explain. So notice that D, okay, has a smaller activation energy, and that's what's going to turn out, that's what it turns out determines how fast it occurs. Remember, that's the activation energy, okay? So our activation energy is higher for A than it is for D. So D is going to be faster than A. Okay? So I'm going to go ahead and erase this so I can go on to the next question. Okay. Okay, so compare energy diagrams A and B. Which process will more greatly favor products at equilibrium, and explain? Okay, so our starting materials on A are higher energy than our products. But for B, our starting materials are equal energy to our products. So B is going to be about even for starting material versus product. For the at equilibrium, the concentration is going to be about equal. But A is going to favor products more greatly because we have a greater delta G. Okay, higher negative delta G. Okay, so this delta G is more negative than here, which looks like it's actually 0, which is going to be a 50-50 mixture at equilibrium, right? So A favors products. Okay, so let's erase this. And we'll do the next one. Okay. Do any of the processes exhibit an intermediate? Do any processes exhibit a transition state? And explain. Well, there's no intermediate here because we don't have the valley, but they all have a transition state right at the peak. Okay. Compare energy diagrams A and C. In which case will the transition state resemble reactants more than products? Okay. That's A versus C. Okay, A is going to resemble reactants, and C is going to resemble products because the energies are closer to those things, respectively. I don't generally ask my students that. I'm sorry. Consider A and B, assuming all other factors are identical, which will occur more rapidly. Did we say that? Oh, okay. It's A and B, which will occur more rapidly. Okay, so A is going to occur more rapidly because we have this smaller activation energy. Consider F says consider B and D, which will more greatly favor products at equilibrium. Consider B and D. Okay, B is here and D is here. D is going to more greatly favor products because we have a bigger delta G, a more negative delta G. Next, G says compare energy diagrams C and D. All right, so let me erase all this junk so I can. All right, so we've got C and D. In which case will the transition state more resemble products than reactants? All right, the transition state is going to resemble products more in C than in D because it's closer in energy there, according to Hammond's postulate. Okay, so that wraps up our discussion of free energy. And in the next topic, we're going to completely switch gears and talk about nucleophiles and electrophiles. So this chapter really should be divided into two chapters, where this part goes with the next chapter and the previous part goes with the previous chapter, in my opinion. But since we just have to deal with it the way it is, so we're going to move on to a completely different topic in the next section.